Hello everyone, welcome to this video on Introduction to Parallel Algorithms. So in this one, we will be using OpenMPI to create a parallel code. This is in extension to our first video in which we perform smoothing and standard deviation operations on a matrix, and in this one, we'll be uh, parallelizing that code to improve its performance, and we will be using OpenMPI for that. So let's go through the objective. Is we will parallelize the code in homework one and using OpenMPI. So how OpenMPI works is that it creates parallel section in a serial code using pragmas, and one of the pragmas that it uses its OpenMP is OMP parallel for. Before going too much details on the OpenMPI part, I will just give you overview of what we'll be doing in this one. So in this one, we will be creating a matrix, and then we will be calculating the standard deviation, and then we to minimize the standard deviation, we will be performing some smoothing operations. So the standard deviation, the procedure to calculate is given over here. So you first of all you calculate the mean, and then you measure how much uh, the array values uh, are far away from your mean. So how much they are different from your mean. So and summation of this will give you the standard deviation, and it's defined like this. And in the smoothing operation, you fix a weight that is called a smoothing weight. And if the value is close to one, then you have a then you have a weak smoothing. Whereas if it is close to zero, then you have a strong smoothing. And how it works is you multiply that weight with your uh, with the array element of target, and then you compute you sum it with the average into one minus weight of the neighboring elements. And in this one, I think we are going to do multiple smoothing operations, and we will be minimizing the standard mean. So a link to the previous video will be provided in the description of this video. So let's go with the code. I think it will be better if I explain it from the code. Yeah. So to enable OpenMPI, you need to include this particular library, omp.h. And initially, right now, there are, I think, three functions. So first one is random array generator. So in this, you are generating a random array. Then there is a sum operator, and then you are calculating the standard deviation. Yeah. And one more is for the smoothing operation. So let me pull out the other code so that we can do a one-to-one comparison between sequential and a parallel code. Let me see. Yeah, so we have, yeah. So this is the original code, and in this one you can see that in the sum you are just creating uh, an array S. Yeah, this is no. Okay, so here is the uh, array generator. So you are using random numbers to calculate to uh, to populate this array, and a scaling is used. And in this, the scale is 10, so your numbers will vary from 0 to 10. Yeah. So if you compare it with this one, Uh, there is one better way to show this. Give me a minute. Yeah, so right now we have a one-to-one comparison. Okay, so oh yeah, so this is a random array generator. So you can see here no parallel section for use, and directly we are doing populating this particular array. But in here we are using OpenMP to parallelize this section. So the syntax or pragma for this is you use pragma OMP parallel. That this actually creates a parallel section, and default none means that none of the variables that will be used and will be shared among different threads, and you will be and we are explicitly sharing the array, the size, and the scale among multiple threads. One thing I would like to bring to the notice is that OpenMP implements a thread-based parallelism, whereas other parallelizing techniques such as MPI they use a process-based parallelism. So in this, it works like a fork and join thing. So let me show you that. Yeah, yes. So there are two type of parallelism. One is thread-based and process-based, and OpenMPI is one which works on thread-based parallelism. And then if we go for, yeah, so to create a parallel section in OpenMPI, first of all, you need OpenMPI library, which is included over here. And actually, this is for Fortran, so it will be a little bit different for C. So, but the basics are same. So, OpenMP parallel creates parallel section, whereas OpenMP parallel do will create a loop, a parallel loop, and in this we are using reduction. So we are summing up each local array which is computed by multiple threads. So let's go to this code. Yeah. So here we are creating a parallel section in which we are seeding the random number generator with our OMP get number thread. Thread number will give you the local thread which is working here. So like thread 0, 1, 2 like that. And the pragma OMP4 it creates a parallel loop and in this way we are generating the array I. So the second one is sum in which we are doing a sum operation on the elements of the array, and in this also we use the same pragma because we are using a for loop in this, so we can include directly in this one uh, parallel for, and default is none, and we are sharing the uh, array and the size, and then reduction is carried out. In this, you can see that we do not explicitly need to scatter the data among multiple threads. This is being taken care by the OpenMP. This is one of the advantages of using OpenMP because it's like you can easily create a parallel code which works, a program which works on parallel computing just by using just uh, minimal by just making minimal changes. So the standard deviation, the mean is calculated, the initial variance will be 0, and then you're using a for loop for calculating the variance. And similarly, the smoothing operations, here you are here again we are using a for loop for carrying out the smoothing operation. This can be combined. We may have to see this, like how to combine this. So as we talked in the theory, we calculate the average of neighbors multiplied with weight, and this is over here. So array plus the weight of neighboring array. And so the size of the array is this. We are using a weight factor of 0.6 and number of iterations are 5. And then we are printing different times. So let's run this program. So to compile this program, we can use GCC. That is, and minus O3 flag is used for optimization, and you need to include this minus F OpenMP for compiler to know that there will be some OpenMP sections. Otherwise, if you see that it comments out. No, it doesn't do that in C. But in Fortran, if you don't specify F an OpenMP, it will just no. Actually, it works in this because in C you use hash to create comments. So if you don't include this, it will just work as a serial code. This is one of the advantages with OpenMP. And then you specify your program and the file name to which it should be compiled, and minus LM is included for math operations. So let's compile this. Mm, Okay, we are not in the directory. Let's go to homework 4. Yeah, now if we run the command, yes, it has compiled. So to run this, you can either explicitly specify the number of threads you want to run, or like on the top, you can see I have specified one thread. So let's just do this one first. So you can see that we have this array and thread, we have the number of threads is 1. So, so after each iteration, you can see the standard deviation is getting reduced. Let's now kick up the number of threads, give it 4. So now you can see that it's much faster, and yeah, much faster because that is our objective. If I go with maybe 16, it will be much faster. So you can time improvement points 0.06 seconds, it is 1.2 seconds, and then with one thread, it was 7 seconds. So if you see the order, it's I think it's close to 3, uh, actually more than 3. So, so this thing, yeah, so you can see that you can easily parallelize your code using OpenMPI. And let's go with the report part. I think I have a graph to show this. So you can see there's a time reduction with the number of threads. It's a exponential decrease in time. So yeah, so I use 1, 2, 4, 16, and 32 threads, and these are the timings. So by using 2 threads, you can get an order of speed up of 2. Again, it's close to 2, and yeah, so speed up is close to 2. Yeah. So thank you all for watching this video, and I'll be sharing this report as well as code implementation on GitHub, and the link to that will be you can find that in the description, and a link to the previous video will also be provided in the description. Thank you. Have a good day.